Right, so can you see my screen?
Yes, sir.
Fine. We'll talk about motion on the 1D today. So motion, an object has in motion when it is basically moving. So that means it is changing its position. That motion we can categorize in the two way. One, we define, say that linear or translatory motion, which would be in a straight line. And second one, we define rotatory or circular motion. You can write the second one, which is rotatory or circular motion. Linear or we will mostly focus on the linear or the translatory motion. Rotatory part we will discuss later, the next coming lecture actually. Alright, so to explain the motion over here, we will only talk about the mathematical description of the particle, so which is known as a kinematics. We'll discuss the different parameter like position, velocity, acceleration, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. This of thing we are going to talk about in this kinematics, which is basically the mathematical description of the particle, but not the dynamics. Dynamics basically describe why it is changing its velocity or position or acceleration, etc. For that one, we have to introduce the idea of force. Since still we did not introduce the force, so that way we are not interested about the dynamics of the particle. We are only interested about that kinematics of the particle. So to explain that kinematics of the particle, we have to introduce some parameter. Say first I am going to talk about that position. Position is the location of a particle at a particular time. Say you have a axis, your Cartesian coordinate system, which is, I can say this is x axis and this is y axis. Say there is a position, say this coordinate of the particle is p position and the coordinate is x and y. Now, or I can say this is x1 and y1. That is the reason I am saying that. Now we can locate that position of the particle from my origin or the reference point in that way, right? We can locate in that way, which that location or the position we can express by a vector, say that r. That vector r I can write, or you can say that this is the r1. I can write, say this is the r1 would be x1 I hat plus y1 j hat, right? That we write by the using idea of the vector triangle law, because this is would be your x coordinate. If you multiply that x coordinate by x I hat, you will find out that vector and as well as that one. That's how actually we can write down that position vector r in the Cartesian coordinate system. Alright, now say that particle is changing its position, say after a certain time, say that particle travel in that path and this is the new position, say that is the q, and q I am saying that is say x2 and y2 is its coordinate. Now then we can write that location of the particle q is by r2, right? So it's the same way we can write this is the r2 and this r2 vector can be written as x2 I hat plus y2 z hat, right? So this is will be my r2 vector. Fine. Now the displacement between these 2 points, say that q1 sorry p and q, we can write that would be the displacement between these 2 particles, which I am going to write by that displacement I am writing, say that del r. Now if I want to find out that displacement, which is a vector actually, if you closely observe the distance from that point to that point, which is a scalar quantity, but the displacement is a vector which has some direction towards that direction. Now if you closely observe at the point P, this R1 is connected in such a way, head of the R1 is connected to the tail of the del R. Then I can write from here, it would be R1 plus del R must be going to R2, right? Then I can write it over here. Now what is
Yes.
del R? Del R would be R2 minus R1. That the displacement I want to find out between the particle, between the point P and Q. Then R2 I find out, which is x2 I hat plus y2 z hat, right, minus R1. R1 is x1 I hat plus y1 j hat, right? This is the case. I just plug in the value of R1 and R2. Then I can find out what would be the del R. So del R would be x2 minus x1 into I hat plus y2 minus y1 j hat. So that would be the displacement between these 2 points. So that means if the particle moves from the point P to Q, then we can find out what is the displacement between these 2 points P and Q, or how much distance does the particle travel. That would be basically the distance, which is a scalar quantity, and we can find out distance would be basically the magnitude of that displacement vector del R. Now if you take the magnitude of that vector, you will find out the distance between the point P and Q, and you know how to find out the magnitude of that vector. Alright, so if it is 3-dimensional, I did it for the 2-dimensional case actually. If it is 3-dimensional, then you can also, you have to add one more component over here. So in that case, the del R would be basically x2 minus x1 I hat plus y2 minus y1 j hat plus z2 minus z1 into k hat. So that would be that displacement in 3-dimensional case. Alright. Now what about, so if I know that displacement of the particle, then I will be able to find out velocity and acceleration also. Velocity we define in general actually that rate of change of position with respect to the time, right? Then we can write down velocity would be, this is actually rate of change of position, is changing its position del R, and del t, which is the rate of change of position with respect to the time. That will give you the velocity, and its unit will be meter per second. And the acceleration right, which is the rate of change of velocity with respect to the time, which would be del v divided by del t, and unit would be meter per second square. So that's how we can find out that acceleration of the particle. And remember, that's actually that general idea we are using over here to find out the velocity and acceleration. So that's mean if you somehow can find out that position vector, you will be able to find out the displacement. If you can find out the displacement, you will be able to find out that velocity and acceleration of the particle. And Speed would be basically that for the case of velocity, you can find out that the speed would be basically magnitude of that velocity vector. Although in everyday language we do not make any distinction between the speed and the velocity, but there is a difference in physics if you define velocity and acceleration, because velocity is a vector which has magnitude and the direction, but the speed is a scalar quantity, it has only the magnitude. But in particular case, speed is simply how fast a car is moving, whereas velocity is how fast and in which direction this car is moving. That's how actually we differentiate between the velocity and speed. In general, if your velocity vector and your acceleration vector are in the same direction, you can say that the car will be speed up, it will be increase will be speed or the velocity. If these two vectors are in the opposite direction, then you can say that the car is going to slow down. And if the say that if the car is moves at a constant velocity, then you can say that that acceleration of that car is going to be 0. If a particle or the car moves at a constant velocity, then its acceleration would be 0, because acceleration we define actually del v, which is the change of velocity, initial and the final velocity. If it moves at a velocity v1 at the first time and v2 at the second time, and these two must be the equal, since it's moving at a constant velocity, then definitely the difference del v would be basically the 0. So that's why your acceleration would be 0 if a particle or a car moves at a constant velocity. Now we are going to define, say that a parameter, that's we define that average velocity. Say you are driving your car with a speed 25 meter per second on the road. Suddenly a pedestrian came in front of your car. You instantaneously slow down the car. Say your speed going to from 25 to 10 meter per second. So that's when you press the brake of the car, and after crossing that pedestrian, you again speed up your car and come back to your original speed 25 meter per second. Say only for calculation, say this scenario happened within a say 1 second. So only for this calculation I am saying this one. Then if I asked you what is your average speed or the velocity, if I ask, velocity will be basically a negative direction, actually I am talking about only the average speed. So average speed would be basically, you will say that in that case is going to be 25 plus 10 divided by 2, that should be 17.5, because 25 plus 10 is a 35, divided by 2 is a 17.5 meter per second. It will be also when you increasing your speed, so that's mean when you is speeding up, 10 plus 25 divided by 2, which is actually the 17.5 meter per second. But interesting thing, in between that two speed, you never, probably that your speed has never 17.5, but it's saying me that if you move in a that speed, you can understand from there, if you start from say that 10 meter per second, after if you move at that average speed 17.5 meter per second, after a while your speed would be 25 meter per second. That's the meaning of average speed or the average velocity. That means the average speed is not the actual scenery of your journey, which is actually that an idea or the estimation, if you move in a that speed, you can reach that location after a certain time. That's the idea of the average velocity. Now, how we are going to calculate this average velocity, or mathematically how we will find out this average velocity? Since we talk about this would be mathematical description of the particle or any system, then how we are going to calculate that average velocity mathematically? Alright, so for that one, I choose a scenario like that. So this is a case. I start from that point. So this is my xt1. xt1 indicate my location at the t1 time. So you start with your brand new car and you choose, this is your positive x direction. So only for calculation I am doing this one. Fine. Then you goes xt2, this is xt3, then you turn back and going to back your original position. So this is actually t4 and say this is actually your t5 displacement or for the position, and this is also corresponding time. So this is t1, t5, this is t4, t2, and say this is t3 time. Now if I want to find out that average velocity in between time, say the t1 and the t2, say average velocity I am writing t1 and the t2, that I'll write down my general definition, which is rate of change of position, right? At t2 time the car was xt2 location, and at t1 time the car was xt1 location, and the difference of the time is t2 minus t1 into I hat. Since it's a one dimensional, so that's why I give that I hat. So that would be basically that average velocity of that car in between time t1 and t2, and we can simplify this one. Actually it would be del x actually the difference in the x direction divided by del t into I hat. So that would be that average velocity definition mathematically. It's a general definition, we can write down in that way. So, and if it is two dimensional, then you have to write this equation will be del x over del t I hat plus del y over del t z hat. So that would be basically your average velocity formula for the two dimensional. If it is three dimensional, you have to add one more, that would be del z divided by del t k hat. That will be the mathematical expression of that average velocity formula. And since this average velocity, we can say for this case it could be greater than 0, it could be greater than 0, it could be equal to the 0, and it could be also less than 0. It would be greater than 0, I can say, if I move in the direction of my positive location. So for example, if I say the average velocity in between time t1 and t2, it will be greater than 0. That means it's a positive quantity. Why? Because since I am choosing in that direction is the positive, so if I move from xt1 to xt2, that would be the difference, that 2 point would be basically a positive number. Definitely x2 is greater than with xt1. So that's why if you take the difference is going to be a positive quantity. So that's why this average velocity in between time t1 and the t2 would be positive, whereas the average velocity in between time t2 and the t4, that's definitely going to be negative, right? So that's why I can say this average velocity in between time t2 and the t4 is going to be less than 0, which means it's a negative. What about the average velocity 0? The average velocity in between time t1 and the t5 is going to be the 0. Why? Because your initial point and the final point are the same, right? You come back to your original point. So that means where you start from that point, you again come back to on to that point, then definitely your average velocity is going to be 0 over here, because your displacement is 0. That's why your average velocity over here is going to be the 0. But what about your average speed? What would be your average speed? Will it be 0?
No, sir.
No, sir.
For the case of average speed, basically I am going to consider the distance, not the displacement, right? So for the case of average speed, I will count down that distance. It will start from xt1 to t2, and again I will add this distance. So that means if you say that distance is 5 meters, say for this, then the total distance would be 10, 5 plus 5, which is 10 meter, divided by how much time it will take from come back again its original position. If you take the ratio of these two, total distance divided by total time, then that will give you that average speed. Although the average velocity is 0 in between time t1 and the t5, but for the average speed is not 0 between t1 and the t5, because average speed basically the total distance divided by total time. Or sometime if you think about, say, if you go from that point to that point and you stay over there some time, and again after taking your break you will come back again over here, in that case you have to also count down whatever the time you spend over there. That would be the case, actually you are going to consider the average speed or the average velocity case, because average velocity is 0, whatever the time you spend, that's not a big deal. But in the case of average speed, you have to consider that time also, whatever the you going to spend over there. So that's how actually we can find out that average velocity. Fine. Now what about, say, instantaneous velocity? Say instantaneous velocity.
স্যার এভারেজ স্পিড কি টোটাল টাইম বলছিলেন অর চেঞ্জ ইন টাইম বলছিলেন?
It's a total time.
ওকে স্যার।
Average speed actually total distance divided by total time. Total time actually, if you take the difference of that ones, that will also give you the total time. Alright, so instantaneous velocity. So instantaneous velocity actually the velocity at a particular time. So you are going to find out. Say, if I say another way, say if you drive your car, into your car there is a speedometer, right? If you ride or drive your car, you will find out that your car there is a speedometer, is a indicator actually, that indicator move back and forth. And when you look at that indicator, whatever the indication is giving you, that would be that velocity of that car in that particular moment when you look at that speedometer, and it would be different at different time. And this is actually the instantaneous velocity. And how you are going to find out that instantaneous velocity? Say for that one, say I'm going to say this is a location of your particle, it's a dot, and you want to find out that velocity of that point or the particle just right after that point, which I indicate by the red dot. Your initial point is the black dot and your final point actually the red dot. So that's mean you are going to find out the velocity of the particle just right after your initial point, which is actually that red dot. Then this distance to travel from that point to black dot to red dot, it will take a very small amount of time, right? Which we say that which is actually the del t, and del t actually tends to 0, is a very close to 0, but not exactly the 0. Then if it is the case, then we can define that velocity definition. That definition we can write, because velocity actually that rate of change of position, right? Del r over del t, that's the general definition. Then its final point actually x t plus del t, so that's mean t plus del t displacement of the particle at t plus del t time, minus is initial displacement, which is start from x t. You understand what I am writing over here? Divided by difference of the time difference actually t plus del t minus t. Can I write this one? Do you understand what I am doing over here? Hello? And we can say del t actually tends to 0. Do you understand this equation?
Yes, sir.
Alright, so I'm going to take a pause over here, give your attendance right now within 1 minute. give your attendance in the chat box, just write down your ID, nothing else, just write down your ID. Right, so your time is up for the attendance. Fine, so that would be actually that mathematical description of this instantaneous velocity. And this is actually the definition of that derivative of this function x. Then we can write this v actually dx over dt. That's the definition of the derivative of that function. Since it's a vector, so that's why I write down this I hat. That will give you that instantaneous velocity of the particle or the car at any time t. That's how actually we can find out that instantaneous velocity. If it is two-dimensional, we'll write v would be dx over dt into I hat plus dy over dt z hat. If it is three-dimensional, I'll write dz over dt in k hat. So that would be the instantaneous velocity in the three-dimensional case. You can find out using that one. Now, what is this? Actually, say physically, if I am to draw, say I'm going to consider a scenario. I'm going to draw a journey. Say the displacement versus time graph of a journey. Say this is one-dimensional, so that's why I draw. So this is my x-axis, and this is my time axis. Say I'm going to label this is time t1, this is t2, this is t3, this is t4, say this is t5, and so on. Say I'm going to say displacement versus time graph of a particle. It's like that. So this is a case. I'm drawing this arbitrary curve actually, displacement versus time graph of a car, or you can say of a particle, is that. This is the case. So this is would be your x1 displacement. So we also say that your, sorry, I should draw the time t1 over t5 over here, not over here. So this is actually your t5. Then this is actually your t4. This is actually displacement at the t2, and say this is actually say t3. You can write, so this is your xt2. This is actually your xt3 displacement, and this is actually your t4 displacement, and so on. This is also your xt5 displacement. The case actually described over here by that curve. All right, say now if you say from this curve, if I take that instantaneous velocity that we define actually by dx over dt, right? What is that actually over here? What is the dx over dt from this curve? From the mathematical point of view?
So
Mm-hmm.
it's velocity, dx over.
No, that's a definition. But what is dx over dt from x versus t curve? From the mathematical point of view?
Um,
Instantaneous velocity.
No, that's a physics point. You were saying that.
represents it represents a square or a rectangular.
No. Can anyone say me what will give me from displacement versus time graph? Say I have a curve like x versus t. From that curve, it could be any curve actually, any arbitrary curve. If I take
Such
dx,
slow.
it's a slope. Dx versus dt is going to give me that slope. That the mathematician will say that it is basically the slope. But we define in physics that slope actually the velocity over here. Right? Am I right?
Yes, sir.
Yes.
Yes, sir.
So dx over dt basically is going to give me that slope of this curve, because if you take the slope, this thing over here, you will find if you take in between time t1 and t2, you will find that the slope would be positive. If you take the slope between t3 and the t4, that's going to be the negative, right? Or t4 and the t5,
Yes,
if you
sir.
take the slope, that is also going to be the negative. So that's why this instantaneous velocity could be also say that greater than 0, it could be also less than 0, and it could be also equal to the 0. Now you will find out the instantaneous velocity is going to be positive when your slope is positive. It will be negative when your slope is going to be the negative. But when would be the 0? At which point the slope of this curve is going to be the 0? I can say the slope 0 would be over here, right? At that point, slope is 0. At this point, the slope is 0. At this point, the slope of this car or the particle is 0, right? If you take the slope in this point, actually, you are going to find that the slope is 0 over here. Fine, because that del x actually is 0 at that point. So that's why your slope is 0. Then what is the physical significance of this slope is 0 over here? If it is instantaneous velocity is positive, I can say I am moving in my positive direction. If the instantaneous velocity is negative, I will say I am moving in the opposite direction of my positive axis. If it is 0, then I will say that basically the car is basically changing its direction. Why? When the instantaneous velocity is 0, we actually dx over dt equal to the 0, then we say that the car will be momentarily stopped in physics. In physics language, when the instantaneous velocity of a particle is 0, we say that the particle will be momentarily stopped. Momentarily stop means is the velocity actually the 0 at that point. And how we explain this thing over here? Say if you move towards that direction with your car, and after suddenly you decided that you will make a turn in the opposite direction. At the turning point, when your slope is 0, then we are finding that the instantaneous velocity is 0 over there. Although you will not find out that difference, because the car make a turn because due to its inertia. That's why car is able to make a turn into that. But the car at the turning point, your instantaneous velocity is 0. So that's why we can say that the car will be momentarily stopped over there. So that's the physical significance of instantaneous velocity is 0 mean. You understand?
Yes, sir.
Yes, sir.
All right. By the same idea, actually, we can also define that average acceleration. So we'll define that average acceleration for this case, say for the time t1 and the t2, that would be basically vt2 minus vt1, because we define the acceleration actually rate of change of velocity with respect to time. So we will define in that way, which sometime we can also write down del v divided by del t, right? Meter per second square is unit to be basically meter per second square. And for the two-dimensional case or the three-dimensional case, sometime we can also write down that average acceleration would be del vx divided by del t I hat. So del vx actually change of velocity along to the x direction plus del vy divided by del t into j hat plus, if it is three-dimensional, I will write del vz divided by del t k hat. So that would be actually that average acceleration of the particle in three-dimensional case. You can use that formula by the same analogy. And it could be also say that it could be greater than 0, it could be equal to the 0, and it could be also the less than 0. Depending on the situation, you can find out this case. And what about that instantaneous acceleration? If I say that instantaneous acceleration, that could be also write down the rate of change of velocity, but just right after your point, we will write this acceleration in a form, say that vt plus del t, velocity, final velocity, this is the initial velocity divided by difference of the time, t plus del t minus t, which I can write, it would be give you the del t, and we define that del t actually tends to 0. It's not equal to the 0, but it's very close to the 0. Then this is actually the mathematical definition of the derivative of a function. This will be the derivative of this function v, which I will write del v over del t. That's the definition. But I know that the v, which is we define in a way which is dx over dt into I hat, right? That's the definition of the velocity. Then we can write this acceleration, it would be d square x divided by dt square into I hat. That would be actually that instantaneous acceleration of the particle at any time t. So that's mean if you just know the position, you'll be able to find, if you take the second time derivative of that position function, you will find out that instantaneous acceleration. If you want to find out the instantaneous acceleration in any desired time, after taking that derivative, second time derivative of your position function, you have to plug in your desired time to find out that instantaneous acceleration using that equation. So, and this if it is three-dimensional, we will extend this equation dt square I hat plus d square y dt square z hat plus d square z divided by dt square k hat. So this would be actually your instantaneous acceleration for the particle at three-dimensional case. And that's how actually you can find out that average acceleration as well as instantaneous acceleration if you just know the position of that function. All right, say now say I'm considering a particle is moving according to this equation. Say that its displacement is given by 8 minus 6t plus t square and meter. So this is actually that particle moving according to this equation. So that means that position of that particle, we can find out this equation. If you plug in the different time into this equation, you will find out that different position of the particle, right? At t equal to 0 second, you will find out x would be 8. At t equal to 1 second is going to be basically 3, right? Because 1 is 6, so 9 minus 6 is going to be the 3. So that means at different time it has different position, it's changing its position. Then I can find out that velocity at any time, which would be first time derivative of the position function, v is dx over dt. I'll find out that is going to be minus 6 plus 2t. Yes, is there any question over here?
No, sir.
So velocity would be, in that case, I just take the first time derivative of this equation, which is 6 plus 2t, right?
Yes, sir.
And the acceleration, that is actually first time derivative of the velocity function dv over dt, or the second time derivative of the position function. I'll find out it is going to be plus 2 meter per second square. Look at this, I use that plus and minus sign. There is some issue actually, I am using that one, I will tell that one. Now this will be my position, this will be my velocity, and this will be my acceleration. Alright, that's great. Now I'm going to find out, say that at some parameter or some data I'm going to find out from there at t equal to 0 second. So that's mean when it is start, what would be its position, or what was its position? I write down x naught, that going to be 8 meter, right? The velocity, which is v
Yes,
naught,
sir.
is going to be minus 6 meter per second, and the acceleration, which is independent of the time. Look at this, there is no t function into that acceleration, so that means it is independent of the time. Then I can say the acceleration of the particle is not going to change, which means that the particle will move at a constant acceleration throughout its journey. If the particle moves according to that equation, I write over here this equation, if the particle moves according to this equation, that acceleration of the particle is not going to change. It means that the particle will move at a constant acceleration, because acceleration will remain same throughout that journey, which is plus 2 meter per second square. It's not going to change with respect to the time, but the velocity will be the change. If you plug in the different time, say if you say the t equal to 1 second, the velocity is going to be the minus 4. So that's when it is changing its velocity.
স্যার অ্যাক্সিলারেশন যদি আমার কনস্ট্যান্ট থাকে মানে চেঞ্জ না হয় তাহলে স্যার ইনস্ট্যান্টেনিয়াস যে অ্যাক্সিলারেশন আর হচ্ছে অ্যাভারেজ অ্যাক্সিলারেশন সেম হবে না স্যার?
If they, yeah, yes, if the acceleration is not going to change, average acceleration will be 0 in that case. You can say that in between any particular time.
স্যার আমার অ্যাভারেজ অ্যাক্সিলারেশন আর ইনস্ট্যান্টেনিয়াস অ্যাক্সিলারেশনটা ক্লিয়ার না স্যার, মানে লাইক ডিফারেন্সটা বুঝতেছি না স্যার আসলে ঠিক মতো।
All right, I'll come to that point actually. So just first tell me that one.
ওকে স্যার।
So this is the case actually, right? So at t equal to 0 second. Now say I want to find out when x would be equal to the 0. So I want to know actually when the particle would be at the origin of my reference axis or reference frame. Since I find out this x actually 8 minus 6t plus t square, if I plug in x equal to the 0, then I can find out at what time it would be at displacement would be basically the 0, right? So that's when it would be at the origin, where I choose that origin. Then if you solve, since it's a quadratic equation, you will find out the 2 root of the x. You will find out that t would be plus 2 and t would be also plus 4 second. I should write down the unit over here, it's a second. I'll take the both 2 root over here because both are positive quantity, right? So how can it possible? We'll do that one. That's very interesting. All right, say, so if I ask when that velocity of the car is 0, because when I start at t equal to 0 second, its velocity is not 0, it was minus 6. I want to know when the velocity of the particle would be 0. Then I have that velocity equation, which is minus 6 plus 2t. If I know when it would be 0, I'll write down v actually minus 6 plus 2t, that is going to be the 0. It means that t would be 3 second. So that's mean at t equal to 3 second, the velocity of the particle would be 0. All right, so now when the velocity is 0, when the velocity equal to the 0, what is the value of x? Who is knocking me at that time? So I know the velocity is 0 actually, that t equal to 3 second. If I plug in t equal to 3 second into my displacement equation, which is that one, 8 minus 60 plus t square, right? In that case, I can say that if you plug in, you will find out that the x is going to be basically that minus 1 meter. That is the case. Now, I'm going to draw that picture of this journey according to this information. If I draw, say, this is my displacement equation, displacement, and this is, say, the time, since it's a one dimension, so that's why I write in that way. So this is actually, say, you can say this is your time scale, which will be in a second, and say this is actually your displacement equation, displacement direction, which is would be in meter. Now say this is actually your t1 second, this is t2, or you could write down the in term of 1 instead of, say, this is a 1, this is 2, this is 3 second, this is 4 second, this is 5 second, this is 6 second, and you can say this is actually this is actually the 8, and this is actually your origin, and say that at that time when t equal to 0 second, your position actually, look at this, when t equal to 0 second, your position actually 8 meter, your velocity is the minus 6, and acceleration was plus 2 meter per second square. Now, since the velocity is negative, then I can say that the car is moving towards that direction, which is actually that minus 6 meter per second, and its acceleration is the plus 2, which would be upward direction, 2 meter per second square, which saying me that one the car would be slow down because the velocity vector and the acceleration vector are in the two different direction. Then I know at t equal to 2 second and t equal to 4 second is displacement is 0. So that's mean at t equal to 2 second, car must be at that point, and t equal to 4 second, car must be at that point. They must be at that point at the time t2 and the t4 second. And t equal to 3 second, I know the displacement is basically the minus 1. So I define, so this is actually that minus 1. Then this is actually 3 second, I can say that the car would be over here at t equal to 3 second. Now if I draw that one, so that's mean the car will be start from that point. When I count down time, at the moment this was my origin, it is start from that point, which is 8 meter positive. Since its velocity vector and the acceleration vector and the two different direction, it will be slow down. Slowly it will follow that path. It t equal to 2 second, it would be over here. T equal to 3 second, it would be at over here, and t equal to 4 second, it would be over here. So that's mean at t equal to 3 seconds, since velocity is 0, I can say it will change its direction from that point into that direction. So that would be basically that trajectory of that particle. So that's how actually we can predict the trajectory of that particle. That means if any particle moves according to this equation, which is the general equation of the displacement of a particle that I write, which is x equal to x naught, or not a, that way I will come to that point. So this one I write, so x equal to 8 minus 60 plus t square, which is a general form of a displacement equation. We write this thing in a that way, x equal to c1 plus c2t plus, I'm sorry, there is some parameter actually over here, and c3 t square. This is the most general equation of a displacement of a particle, and where c1, c2 and the c3 basically the constant, I'm going to find out that value of this constant over here. So first of all, say if I want to find out, say that the velocity, I'll take that first time derivative of this equation, which would be dx over dt, and this is going to give me actually, since c1 is constant, it will be 0 plus c2 plus 2 c3t, right? I'll find out this equation. That means the velocity actually c2 plus 2 c3 into t. So this will be my velocity equation. And the acceleration equation, which is actually first time derivative of the velocity dv over dt, then I can say c2 is constant, this is going to be 0 plus is going to be 2 c3, right? Now I'm going to find out that one. Say if I plug in into this equation, say I'm going to plug in at t equal to 0 second into this 3 equation. So position, velocity and the acceleration equation I write over here. Then I can say this x naught is going to be basically the c1, because if you plug in this c2 and c3 is going to be cancel out from this your displacement equation. So that's mean c1 would be basically the x naught, and this c2 is going to be v naught, which is would be c2. I can write the v naught actually that initial velocity is a c2, and this c3 is basically independent of the time, right? I can find out it would be half of a equal to that c3, right? Because this c3 actually independent of the time, it doesn't depend on the time. So that's why it would be constant over here. I find out this value of constant. If I plug in this c1, c2 and c3 into that equation, then I will find out this displacement would be x naught plus v naught t plus half of a into t square, right? Because I find out the value of c1, c2 and c3 and I just plug in into this equation, and this is actually the most general equation of particle in the case of the motion displacement equation. We can write in that form. Sometime you will find out we will write on this equation in a form. This would be x naught v naught xt plus half of a xt square, which is v naught x actually the initial velocity in the x direction. If it is one dimensional, we will use that one. If it is two dimensional, I will write on this equation in y format, y naught v naught yt plus half of ay t square. That would be my displacement equation along to the y direction. What about the z direction? I'll write this one z naught v naught z into t plus half of az into t square. So that would be, which is the same equation, right? We write down in different directions. So that would be the most general equation of the displacement of a particle. Using this equation, you can define any type of motion, 1D, 2D, 3D, or whether it is a projectile motion, or it is whether the particle is moving as a constant velocity, constant acceleration, or neither nor. Any type of motion we are going to explain by this equation. So that's why this is one more important equation. Remember, this is very useful equation and very important equation. One of my favorite equation in this mechanics chapter. Only this equation can explain any type of motion over here. So that's why this equation is not new for you. Probably you use that equation of motion in another way, which is h actually ut plus half of at square. You know this equation, right? And you define v equal to u plus at, or v square actually u square plus 2ax. You use these three equations when the particle moves at a constant acceleration. And this equation is not new. It's all three equations could be derived only from this equation. Because in that case, if you consider x naught actually the 0, you will find out this equation x actually v naught xt plus half of axt square, which is exactly the same equation u plus ut plus half of at square. But in that case, you consider the car is start from your origin, but that cannot be happen in some time. It could be start from different location, like this. I give you that example. My origin is over here. I consider that origin of that particle over here, but the car start from initially at 8 meter, which is actually the x naught, into my that equation. So that's why it would be better to think in that way. This is the most general displacement equation. We can define whether the particle moving at a constant velocity or not, or neither constant acceleration. So how we can define that one? Say if I write this equation, say the particle is moving according to this equation, say that 2 plus 3t plus 6t square. Can anyone say me whether the particle move at a constant velocity or constant acceleration or neither not?
Sir, it be constant acceleration. It would be constant acceleration.
It will be constant acceleration. Why it is so?
So if I find the second derivative of x, it would be only 6.
Second derivative of this. So look at this. So first I will check that whether it moves at constant velocity, which is v dx over dt. If I take 0 plus 3 plus 12t, right? Velocity I will find out. It would be 3 plus 12t. So that means there is a t present over here. If you change the time, the velocity will be the change. At t equal to 0 second, it is 3 meter per second. At t equal to 1 second, it is going to be 15 meter per second. So that means it is basically changing its velocity, right? V naught constant over here according to this equation. All right, what about that acceleration in that case? I'll write, so dv over dt, first time derivative of the velocity function, or the second time derivative of the position function. Then I'll find out 0 plus 12, right? Which is right now independent of that t. So that means if you change the time, the acceleration is not going to be the change. It will be the remain 12 meter per second square. So that's why I will say the particle which moves at a constant acceleration, not the constant velocity, right? What about, say, instead of that, if I find the equation is like that, x equal to 2 plus 4t cube, what would be case in that case?
It won't be a constant acceleration.
It wouldn't be constant acceleration, right? If you take that second time derivative of that function dx over dt, you will find out there will be a t, because the power is 3 over there. We find out when I take the second time derivative, there is a power is 2, so that's why this t is vanish over there after taking the second time derivative. But over here the power is 3 of t. After taking that second time derivative, there will be also 1t into that equation, which means I'll find out that this equation is not going to be independent of that t. It will be depend on the t. Then I can say the particle is not moving at a constant acceleration at all. Its acceleration will be the change with respect to the time. That's why this equation, if you just closely look at this equation, you can also say that whether the particle moving at a constant velocity or constant acceleration or neither not. Even though the projectile motion I am going to explain only by this equation, using this one. I don't have to memorize those equations, maximum height or maximum range, whatever the equation you memorize. You don't have to memorize those equations. You can just use this equation, you can solve any type of situation. We'll talk about this thing in the next class, actually, 2D motion or the projectile motion. All right, let's think about, say, what would be actually that curve of this case when the particle actually the moving at a constant velocity or constant acceleration, or the free fall case actually. So first I will consider that constant velocity. Say if a particle moves at a constant velocity, in that case, what would be that equation? Probably you use this equation s equal to vt, right? In the case of constant velocity. But I will write my equation would be x would be v naught xt, which is exactly the same equation. V actually that your velocity in the x direction, over here v naught x, initial velocity along to the x direction. We have to mention that one. How this equation become This is actually, I can write from this equation, my general displacement equation, x equal to x naught v naught xt plus half of axt square. If a particle moves at a constant velocity, what would be its acceleration? If a particle moves at a constant velocity, what would be its acceleration?
0.
It will be 0, right? Acceleration is going to be the 0. If I consider that its initial displacement is also 0, then I'll find out this equation would be v naught x into t. So that would be my equation, which is exactly the same equation, this one. So that's mean from that equation I can also find out this motion. Then we can draw that curve, the velocity versus time graph. So this is actually that velocity and this is the time. What would be that curve? It would be a straight line parallel to the x-axis, right? So that means it's not changing the velocity with respect to time, it will be the remain same. All right, what about that, in that case, the displacement versus time graph? What would first I'm going to find out, say, that acceleration versus time graph, then I'll find out the displacement versus time graph. What will be the acceleration versus time graph if the particle moves at a constant velocity?
Be a straight line.
Yeah, straight line. The acceleration is 0, right? You can say that acceleration into that line over here. Acceleration is
Yes,
0
sir.
over. Acceleration is 0 over here, right?
Yes, sir.
Fine. What about displacement versus time graph? So this is time. Say that this is my x. What would be that displacement versus time graph?
It would be maybe the straight line of x equals to y, the way we write it, from 0 to.
Yeah, look at this. If I write my general equation, x equal to x naught plus b naught xt, say that x naught is 0, then this equation I can write, it is basically y equal to c plus mx. Can you write y equal to mx plus c equation, this one, in
Yes,
that
sir.
form? Then this straight line would be in that form where this one would be basically my x naught and v naught x, which is the slope of that curve, that thing is going to be dx over dt, right? So this will be actually that displacement versus time graph. If you say that it's passing through the origin, then you will find out this is will be your x equal to vt curve, if it is passes through the origin. If it is not passes through the origin, then this will be your curve, this one. If it passes through the origin, then this is will be actually your equation, x equal to vt. That's how actually you can explain that position versus time graph, displacement versus time graph, or acceleration versus time graph if the particle moves at a constant velocity. Now what about is the constant acceleration case? Say that constant a. First I'm going to draw for, say, that acceleration versus time graph. So this is my time, this is my acceleration. So it would be some value actually, it's not right. So this is the one value actually. That would be your acceleration versus time curve. What would be that velocity versus time graph? What would be the velocity versus time graph? In the case of velocity versus time graph, I know that this equation, I'm writing this general equation, v naught xt plus half of a t square, axt square. So velocity versus time graph, basically I'm going to take that first term derivative of this equation, which is dx over dt. That's going to give me v naught x plus is going to be axt, right? If you take that first term derivative of this equation, you will find out this one. So which is v equal to v naught x plus axt, which is again y equal to c plus mx equation, then I can say where mx is the slope, and I can write, so this is will be that curve, where if you take this slope, which is actually dv over dt, that will give you that acceleration, and this curve actually would be my v naught, and it would be towards the x direction actually if you consider in one dimensional case. So that would be actually velocity versus time graph if a particle moves at a constant acceleration. Alright, now what about the displacement versus time graph? What would be that? So this is actually your time, and this is actually your displacement in the one dimensional. I am talking about right now one dimensional case. What would be that? Displacement versus time graph if the particle moves at a constant acceleration. Any of you have any idea? Alright, look it over here. Say this is my equation, x equal to x naught v naught xt plus half of ax t square. Say only for simplification, I consider it is start from the 0, initial velocity is 0, and is initial displacement is also the 0. Say for only for simplification of that one. Then I'll find out this x is going to be half of ax t square curve. Now this ax is constant, then this whole term is going to be the constant, then I can say this will be x will be directly proportional to t square. So that's when it's a t square curve, or y equal to x square curve, which is would be in that case actually it would be that one. So displacement versus time graph would be basically in that one. That would be the case actually. You can draw that the different curve for if the particle moves at a constant velocity or constant acceleration. Alright, what about in the case of free fall? In the case of free fall, so I know in the case of free fall actually I'll use that, what would be acceleration versus time graph. So in the case of free fall, we know that the acceleration is minus 9.8 meter per second square z head, right? Am I right? This acceleration is negative actually. So that's why if you say this is actually your time graph, this is actually your acceleration, I'll say this is will be my acceleration over here, which is minus 9.8 meter per second square. It would be always negative. Remember this thing. I'll talk about this thing in the next class because right now your time is up. And what would be that velocity versus time graph? So velocity versus time graph is basically starting from the case of free fall. So this is your x-axis, or you can say that velocity vx, and this is your time. So if you drop the particle, that would be actually your velocity, right? This is the case. Or if you throw the particle in the upward direction, in that case that velocity would be, initially it will be start from a point, which is this is actually the vx. It will be start from the point and gradually it will be decreased. At the top point its velocity would be 0, which is this one, and after that it will again come back to the downward direction. In that case that would be actually the velocity versus time graph if you throw a particle in the upward direction. Alright, so that's how actually we can explain the motion in the 1D and the 2D in that point. Alright, so do you have any question over here? Alright, I'm done for today. We'll explain this thing in the next class. We'll do some problem depending on this situation. If you don't have any question, you can leave, guys.
স্যার আপনি কি আমাকে একটু ইনস্ট্যান্টেনিয়াস ভেলোসিটিটা আরেকবার বলতে পারবেন?
All right. So in instantaneous velocity, basically the velocity at any particular moment. Say you have a position of a particle over here with this black dot, I drawn it over here. I want to find out that velocity of that particle just right after that point, which is that one. Although I draw a bigger point, it's not would be that, it would be, you can consider a dot between two dots. You're going to find out that velocity into these 2 points. Then these 2 points are very close to each other. So how we are going to find out that mathematically of that one?
স্যার স্ক্রিন দেখা যাচ্ছে না।
Oh, I'm sorry. Now can you see it right now?
ইয়েস স্যার।
Alright, so I say this is the one point, the black one, and another point actually this red one. You want to find out the velocity in between these 2 points. Although I draw is a bigger point, it should be not like that, it would be like this one. I draw a small dot one and the black dot one. So say you want to find out that velocity in between these 2 points. In these 2 points the displacement is very small, as well as the time difference is also very small, which is we say that the del t actually tends to 0. This means that close to 0 but not exactly the 0. Then we define that velocity definition, which is final position, which is xt plus del t. So that means the displacement at a time t plus del t minus initial position xt, which is the change of the position, divided by the time, which is t plus del t minus t. And we say that this limit is a condition del t would be tends to 0. It means that it's not 0 but very close to 0. Then we write this equation, limit del t basically tends to 0, which gives me xt plus del t minus xt divided by del t. And this is actually that mathematical definition of the differentiation of a function x. So that's why we can write this one actually dx over dt, and that will give me actually the instantaneous velocity of a particle at any time. It means that if I know the position of the particle, if you take the first time derivative of that position function, you will find out that instantaneous velocity of that particle at any time. After taking that first time derivative of the position function, if you plug in the time, your desired time, then you will find out that instantaneous velocity of the particle at that time. So that's how actually you find out that instantaneous velocity.
ওকে স্যার, থ্যাংক ইউ।